Yeah, so today we um, discuss PC and autoencoders. I mean, today I think it's I mean it's very easy, so I should be able to finish it quickly. So I mean, before going here, let me give a quick overview of this autoencoder thing. Okay. And how it connects to PC. So basically, any input, let us say some input. Okay, some input, and you are passing to a network. Some network, okay, some neural network, and you are creating uh, some representation H. Okay. This is also a vector. This is also a vector. Say this is D. Say this is P dimensional. P cross one and D cross. This is X. And now, um, typically you can call it as encoder. Okay. The encoder network. And this thing goes to a decoder network. Right? Decoder network. And here you reconstruct your X. So this is something, this is your X hat. Okay. And finally, what is your objective is to minimize this difference. Right? So this is theta call, this is some phi. I mean, this represents some say neural network. If it is neural network, it represents neural network weights, and you minimize this loss with respect to theta and phi. Yeah, this is the general autoencoder. Now, if it is P greater than D, right, I think it is called um, overrepresented, and P less than D it is underrepresented, right? So this is what is autoencoder is. So why do we need this? I mean, there is an input again. You are creating some hatch again, going back to Excel, right? So the thing is, uh, by doing this, you learn a powerful representations about the input, especially if P is less than D. Um, Now this H has all the information about X that can be used to reconstruct X. So it's sort of compressing your input. Um, Not just compressing inputs, it learns some complex features about the data, such as image and all. Um, so how it is connected to PCM? So remember last time we discussed PCA from the point of view of maximizing the variance, right? You have some data, let's say something like this, right? And we what you do is it projected this thing here, here, and then you maximize the variance, right? This is the variance. You want to maximize the variance. So by maximizing the variance, you are able to find this uh, line as the direction on to which to project. So there is another interpretation of this PCA is the reconstruction error. So basically, let's say you have input X, which belongs to d-dimensional space, right? The dimension is d cross 1. I want to compress this to a low dimensional, say P, to a matrix. W is P cross D, right? So W times X is the lower dimension. But again, when you want to reconstruct it, you do D cross P matrix. Again, you want to come back to D-dimensional space. Right. This is your reconstruction, right? So X minus X hat, same thing. You minimize them with respect to U and W. So this is another interpretation of PCA, like autoencoder kind of style. Right. So what is the difference between this and this? The PCA is only the linear um, uh, representation, right? So this is your representation, W times X. But in this case, it's not. It's a complicated representation. It is learned by optimizing your uh, reconstruction error through some complicated internet. Okay. So yeah, this is all background you need to know to solve the today's problems. And they're very easy actually. Okay then. So let's uh, go to the problems. Why is this happening? Can you see my slides? Yes, no. Okay. So yeah. So first question is what is the main purpose of hidden layering and the complete rectangle? That means the representation vector as the lower dimension and the input. Right? So obviously to reduce the number of neurons in the network or to limit the capacity of the network. And Okay. So, second question is which of the following problems prevents us from using autoencoders from the task of image compression? Um, right, this is uh, uh, I mean, what happens in an autoencoder is you take a high dimensional input and compress it to very low dimensional ones, and then reconstruct it back. So typically, what happens is that you lose the quality of image. Right. So another, what is the advantage of overcomplete autoencoder or in general any autoencoder, right? Is you learn the more complex nonlinear representation about the input. Yeah. So as I discussed, like what are the primary advantages of autoencoders over the PCA? And autoencoders can capture more complicated relationships of the input data, not just linear ones. Again, like which of the following is a potential disadvantage of using autoencoders for dimensional reduction over the PCA? Right, so basically PCA is just optimization over two matrices, right? Unlike neural network. So it's not computationally intense. And for autoencoders, you need more training data to fit the model. Another issue is the autoencoders may overfit the training data. If data is limited, they overfit the training data and that leads to poor performance on the. Yeah. So, what is the primary objective of sparse autoencoders and how it is different from the usual autoencoder? Right. So basically, any autoencoder learns the low dimensional representation, but the objective of sparse autoencoder is to extract the most important variations in your uh, feature data. I think there is one question. Let me see. Will overcomplete autoencoder lead to overfitting? Actually, it's not about overcomplete or undercomplete. Overfitting is more um, attributed to the amount of data and the size of network. That is true for any network. I did that answer. Okay. Yeah, and this is again very simple question. Which of the following network represents an autoencode? Right. I mean, this is very simple, right? You could have seen this. The input, there is some network, very simple network, and there's an output. It is of same size, right? Uh, yeah. So again, right, if the dimension of hidden layer is more than the dimension of the input, it's called as overcomplete order. That's also a forward. Yeah, this is okay, little bit interesting question among what we have all discussed today. Suppose we have one data point and we have these features, right? Um, this is your input essentially, right? This vector minus 2, 12, 4.7.60. Which of the following functions should be used on the output layer of autoencoder? You want to reconstruct this. Why do you think I mean, I have shown the answer as linear. Why do you think the others are not suitable?
ReLU, it will not be having negative values, sir. It will have only positive
Right, good,
linear values. And
correct,
tan
good,
H, it is -1 to 1.
right,
And logistic, it is 0 to 1 also.
right. Yeah, so that's
That's
why
why it
you
is
cannot
linear.
use, yeah, any of these first three things. Okay, and then the last question is this thing. Right? If the dimension of input layer is under complete, I mean, means under complete means your hidden size is lower than the input size. Which of is the possible dimension for hidden? The obvious answer is 2, because 6 is over complete and it is also over complete. Right? 0, we don't have typically. Right? 0 means it's a kill thing, right? That's out of question. So 2 is less than 6. Yeah, and I think today's was very easy. I can answer if you guys have any other questions. I'll try to answer.
Can you repeat 7 and 8?
7 and 8. 7, it is pretty obvious, right? Why? What is the problem with 7?
Then all are art encoders.
No. What is autoencoder, right? You are reconstructing your input,
Yeah.
right? So which of the following is the uh, which of the following network is doing that basically?
Only B then in this case.
Right. Yeah, that is what I said.
Sir,
And yeah,
in this case,
right.
if the input layer is 3 neurons, and
Hmm.
let me assume that hidden layer is 2, and hidden layer is 4. Hidden layer is 4 and input layer is 2. Whether it will represent
Okay.
autoencoder?
What
In
is the
that case
final
also,
reconstruction?
reconstruction,
2
final output layer is 4 neuron.
or 2, right?
Is 4 2 4.
How can you
Sorry,
count
2 4 2.
four-dimensional? How 242 is an autoencoder, right?
It is an
2 years
autoencoder, sir. But
it is.
hidden layers are more
Yes,
than
yes, it
that
is
of.
autoencoder.
Oh,
Yeah, so wait, so that's why they have given a name that overcomplete autoencoder.
Okay, sir. Sir, in case of autoencoder,
Yeah.
hello? Yes, sir. Sir,
Yeah. Please. Yeah.
in case
Yeah,
of
I'm able to
autoencoder,
hear.
yes, sir. The main application will be we can extract the important features as well as we can reduce the noise. Whether we'll have data compression, sir.
Data compression is also there. That depends on the quality of reconstruction. What I mean is, suppose you have um, you're able to tune an autoencoder such that your reconstruction is good. Based on any, let's say, on whatever you have trained, right? So for that data, you can use it as a compressor. But in general, um, it is not because when you train a network, you want to deploy and use it for unseen data, right? So there it may not be as good as what you have trained on. So that is one application you can have at the back of your
So we cannot include data compression, isn't it, sir?
own. No, but it does compresses the data. And it does represent some proxy, low dimensional proxy of your data, right?
Okay,
Now,
sir. Okay.
it depends on your use case. If you can tolerate that reconstruction, then it is fine, right? So,
Okay. But other two we'll be having, isn't it, sir? Extracting important features and reducing noise.
yeah. Yeah.
Okay, sir. Thank you, sir.
Yeah. Any other questions? 7 and 8, right? Eight is very simple because if you have a hidden representation more than your input, right? So that is called as overcomplete. And if it is lower dimensional than your input, it's an undercomplete. And if you have very few of them present, okay, that's a sparse. And yeah,
What about complete, sir?
probably that's the same size, I guess. Input and hidden layer.
Both, if both are equal, sir, or
Equal, I think. Yeah.
okay.
The last three are pretty obvious, but I'm guessing the first one. Okay. So, any other questions on this? Not on this, any other previous week's topics also you can ask. I try to answer because we have time today.
But when you see you are saying under complete,
Yeah, that means input is greater than your hidden size, which is 2. You want an undercomplete autoencoder and input size is 6. And what is the hidden layer size? Anything below 6 is fine. Of course, 0 is not allowed. That means then there is nothing. Right? So it's the only answer is true.
okay, okay.
Sir,
Yeah,
now what will be the role of decoder in case of autoencoder, sir?
so typically, decoder is, let's say, uh, in this case, I think it is only used for training. And then you can throw out because all you want care about is this representations, right? If you want to do any downstream tasks, that means they classify inputs and all, then you only need after training you only need these representations and fix everything else and then train a simple linear layer to do the downstream task. Typically, that is thrown. The decoder is thrown after training.
So we will be having completely new data.
Okay.
Whether we'll be having completely new data, sir, in that case?
What do you mean by completely new data?
New data, the data will be input data will be transformed.
Yeah. So you only have hidden vectors, right? No, on these hidden vectors, you do any classification and all, right? Because you have learned them pretty well. And it has all the information about your input because from that you can reconstruct uh, right, the original ones.
Okay. From decoder, we can reconstruct the original data.
Yeah, yeah. But that is typically used in training only for downstream tasks, you typically have these representations.
Okay, sir. Okay, thank you.
Okay. So can stop recording.